Right, so we basically had a whole half lecture then on establishing a little bit of vector calculus. And so in particular, having done that, we convinced ourselves that we can take the gradient of a scalar valued function on a more dimensional space, and that is something which is equivalent to a vector valued function, right? It's something which, if you dot it with a vector, gives you a scalar, so that's a vector valued function. And we gave ourselves a divergence operator, and the divergence operator, which is a derivative operator, which, if we have a vector valued function, gives us a scalar valued function. And we worked out how to integrate by parts. So we worked out how to give ourselves that function. So now we're going to go back to the very beginning, and we're going to do the same problem again, only this time we're not going to restrict ourselves to being in one dimension. So the form originally of the problem that we wrote down on day one was that grad squared psi equals f. I have about a 95% track record of getting the sign in this problem wrong, but I'm pretty sure it's minus grad phi equals f. And this is going to be for find some function phi which is in a suitable function space V, and the such that phi takes that's not quite right. I don't want to take all of Rn. Phi takes points in some boundary, some domain which is a subspace or a subset, of Rn, and gives us numbers. Right, then that operation is correct. Given f, and f is also a function which takes our domain and gives us numbers, the number at every point in the domain. And once again, we have two sorts of boundary conditions, although actually in this lecture I'm only going to look at one of the two, and I'm going to punt back the other one until we've worked out how to do Dirichlet conditions properly in more than one dimension. But we can write down what those were. So I can write down that I can have a gradient at the boundary. So previously, in one dimension, I just wrote that d psi dx at the boundary was equal to some value. So now when we're in more than one dimension, so I've got some funny domain, what it means to specify the gradient at the boundary in the same sense that we did it in the one-dimensional case is to specify the gradient in this direction, right? To specify the gradient in the direction that goes out of the boundary. So that's the gradient of psi. So remember, the gradient of psi is something that works in any direction, and I'm choosing it in the direction going out. So n is the outward pointing normal to the domain, and that's equal to g. So g is another function. G goes from omega to r. And the other alternative is, instead of saying how the function changes at the boundary, I can say what it is at the boundary. And that will be a Dirichlet condition. So this is going to be on gamma n for Neumann. And the function takes the value h, which is another function from, well, really, I don't need this everywhere, although it may well be true. From the Dirichlet part of the boundary to R. And so what I'm going to do is I'm going to form the weak form of this equation. And so how do I do that? I choose a suitable test function, and I integrate over the domain my equation multiplied by the test function. And as we've learned before, we typically are only interested in using the test functions which have at most one derivative. In fact, in a future lecture, we might get to the point where we're talking about test functions that don't even completely have one derivative. But we definitely don't want to place a set of handcuffs on ourselves that says that we need two weak derivatives in order to do this problem. So we're going to integrate by parts, so that in the weak form of our problem, we only have we only have expressions in one derivative. So that means I'm going to find psi in V such that the integral, so remembering our integration by parts formula before, right? So I get grad phi dot grad psi dx minus, this time, that's just the way the signs work out, the integral over the boundary, I'll split the boundary up in a minute, the integral over the boundary of phi grad psi dot n ds equals the integral over the whole domain of f times phi x. So that's the weak form. And now we have to worry about what happens on the boundary. Oh yeah. For all phi in V, where V is a suitable function space. So what I'm going to do for the purposes of this lecture is I'm going to assume that gamma D is equal to the empty set. Okay. So that I don't have to worry about it. We're going to come back and do that when in a subsequent lecture. Because when I come back and do that, I will basically explain the documentation that I've been writing for Friedrich in the last couple of weeks and explain how that works. So for current purposes, we'll assume, therefore, that our whole boundary is the Neumann boundary, so that we've specified gamma n equals g. Those of you who are paying attention, close attention, will realize this makes the problem ill-posed. For our current purposes, that's not a relevant problem. And so what does that mean? It means that everywhere on that part of the boundary, I know what this expression is. This expression I've defined to be g, and g is something I know. G is an externally imposed input. So the way I impose the boundary condition is I find this expression, which is here, and I rub it out, and I say that is g. And if I wanted to be neat about this in a kind of Friedrich solve or Dolphin solve sense, I'd move that expression over to the other side, because this now looks like the forcing term, right? It doesn't have the unknown function in it. So if I choose a given test function, then I know what this is. So that is in common with this one. If I choose a given test function, I know what it is. And different from this one, even if I choose a given test function, I still don't know what this is because that's unknown. So now the next step in this process is completely the same as 1D. So what happens is we have our function space V, and in order to do the finite element method, we take VH, which is a suitable subspace of V, such that VH is finite dimensional, and still at least C0 for one time weakly differentiable, right? That's the same as what we did before. And so in particular, if you need a mental image, then VH being the space of piecewise linear functions on triangles, where they're all continuous at the edges and line up. But notice, they're not differentiable at the edges, right? When I go over the edge of a triangle, I get a kink. So it's not fully differentiable at that point. But as we discovered previously, we don't need that, right? So in order to take a weak gradient, we only need continuity. And we did that in one dimension before. It's true in more dimensions as well. In fact, I keep hinting to this, we need slightly less continuity than that, but we'll come back to exactly how much we need on a subsequent occasion. And so now, having done that, I can write that phi is equal to phi I. What am I going to call my basis functions? Omega I, right? For a set of basis functions, and psi is equal to psi I omega I, because they're both in V, right? So they're going to be in the same subspace of V. So they have the same basis functions, different coefficients. That's how I get two different functions in the same function space. And exactly as we argued before, right? So we need to make this expression true for all phi now in the subspace VH, right? But let's have a look at this. As usual, multiplying, so if I take my differential equation and multiply it by a test function, I get an expression which is linear in the test function. And how do I know that's always the case? Well, before I multiplied by a test function, this thing was constant in the test function. So if I take a constant and multiply it by the test function, I get something that's linear in the test function. And that's always going to be true. And integrating by parts doesn't change that. So there's two ways you can see that integrating by parts doesn't change that. The first one is just to observe that integrating by parts was an equal transformation on the equation, right? So it can't possibly change whether the equation is linear or non-linear in one of its arguments. Otherwise, you'd get a different answer. So it wouldn't be a legal transformation to do. So that's one argument as to why that's true. The second argument is you can also just see it by inspection, right? So that's still linear in phi. That's still linear in phi. And all of the gradient operators are linear operators. So that's still linear in phi as well. So what that meant, if you remember last time, is that I can write any expression phi in terms of the basis functions wi, and I can split the equation up. So I can say that, so if this is so this is some random phi that I choose, I can write this out as a sum of integrals where I put wi in here and take phi I out the front in each case. Right, so I can always reduce it down to sums of integrals where the integrals just have this for phi I. That's not always true for the unknown variable, right? It's true in this particular case because this is a linear equation. But in the nonlinear case, it might not be true for this one, but we don't need it to be true for the unknown. We need it to be true for the test functions. And the reason we need it to be true for the test functions is, okay, so I can always, whatever test function I choose, I can write this out as the sum of integrals in the basis functions, where the basis functions take the space of the test functions in all of these. Conversely, that means that if this equality holds for all of the test functions, it is for all of the basis functions, then it holds for all the test functions. Right? So let me write this out in another way. If I move this over to this side, so if I say that this is this term minus this term minus this term, I can write what's called the residual. So the residual is f of phi and omega equals 0. Right? That's just this expression again. And I should have written these two the other way around, because the important point here, using the notation we used earlier, is there's a semicolon. This guy is linear in this one. So that means that whatever phi is, an equivalent expression is the sum of phi I f sum over I psi phi right? Those two are equivalent. Because we're linear in this operator, right? So I can split this up into a sum inside here of wi phi I. That's just what I've written here. And then because it's linear, I can take the phi i's outside, right? I can take the scalar outside. So now that means that if f psi omega I is 0 for all of the wi's, then it doesn't matter what these are. Right? Then that's just a linear combination of zeros and it's 0. So it's sufficient if I can do it for all the basis functions. It's the core trick in the finite element method that actually enables us to get a system of equations to solve. So that means that what I've done is I've turned my system into f right, for all wi in the basis. Of my discrete space, my system of equations. And in the case we're looking at the moment, we're linear. So in the linear case, which is the easier case, we're going to do the nonlinear case in the future. A lot of today's lecture, all the scary different derivative stuff at the beginning, was kind of softening you up for how we do the nonlinear case. But let's just worry about the linear case now. So if we are a linear case here, then what we can do is we can write this, well, we can always write this as psi I wi, but if we're linear in this argument, which we are in this case, right, this is a linear function of this argument, then we can bring the psi I outside as well. So now I get, so I need to use two different indices, right? So we'll call this j, because they're not, this index is not the same as this one. So I get f of wj wi psi j equals 0. I've cheated slightly there. Okay. So this term is linear in psi. Obviously, this term isn't. Right? There's no psi in there. It's not linear in psi. It's just a constant. So I actually need to split this into the same notation we used before. Right. Split this up into a linear bit and a right-hand side bit. And using exactly the same notation we did before, that is just saying that A of psi phi equals the integral over the domain of grad psi dot grad phi. Probably written it the other way around, but it's a symmetric operator. And L equals, so remember I was saying this is kind of like a boundary condition operator, right? It doesn't have any unknown in it. So L is equal to the integral over the boundary of the boundary term, phi g ds, plus the integral over the domain of the forcing term, okay, so now what I can write more correctly, A of omega j omega I equals phi j times phi j equals so what is this? This thing is a linear operator in two unknowns, which is a matrix. This is a series of numbers, which is a vector. Right? For each wi, I get a number here. So I get an I-long vector of them. So that's the right-hand side. And over here, for each row of this matrix is one test function, which corresponds to the test function I put in the right-hand side, and that gives me one equation. And each of those equations has A for wj wi times this. And that's a dot product, right? It's a reduction over j. So this is A times my basis function phi equals my matrix L, where phi is just the vector whose entries are phi I, and L is just the vector whose entries are L at omega I, and A is just the matrix whose entries are A at omega j omega I. So just like the 1D case, all we've really done is written out vector derivatives and done exactly the same things, and we've got ourselves to a linear system to solve. And so now there are basically three parts of what actually goes on in a piece of finite element software. There is the part where we visit elements, and on each element we calculate contributions to A and L. There's the part where we take those contributions and put them into the global A and L. And then having built A and L, there's the part where we solve that. And we use standard linear solver packages to do it. So Firedrake always uses PETSI. Fluidity always uses PETSI as well. So That's kind of pretty standard. I am kind of tempted to call it a day there, because what we're going to get into now is how to actually do that evaluation, and that's where we get into how you get the Jacobians and what the Jacobians actually do, and that's not going to happen in 5 minutes. And it's also kind of rather critically important for a bunch of people to understand that. It's one of the really important parts about how we implement this. So I think we might stop there, and we'll come back to further multi-dimensional stuff next week, and we'll get Jacobians and actually work out how you build systems.